Hi folks, welcome to another review session for Calculus 1. Today we're going to be talking about applications of derivatives, and so we're going to get into related rates, L'Hopital's rule, optimization, curve sketching, and a slew of other things there. So what we'll start with is some related rates problems, and without further ado, let's get started. We have two carts, A and B, are connected by a rope 39 feet long that passes over a pulley P. The point Q is on the floor 12 feet directly beneath P, and between the carts, cart A is being pulled away from Q at the speed of 2 feet per second. How fast is cart B moving towards Q at the instant when cart A is 5 feet from Q? Okay, so when looking at this, the first thing that comes to my mind at least is to do a drawing. May not be yours, but diagrams tend to help us. They aren't always needed, but a lot of times they do. So with that in mind, I'm actually going to try and draw this scenario. So we have this pulley, and we'll say P right here. So that's at the top of our diagram. So we have a pulley P sitting right here. Okay. The point Q is on the floor 12 feet directly beneath P. So if we have a right angle, and I'll draw that. Don't let your eyes fool you, that's a perfectly straight line right there. But so then we have this point Q right on the floor, and then we know that this distance from here to here is 12 feet. Okay, and so two carts A and B are connected by a rope 39 feet long over the pulley P. So we have, we'll draw cart 1 right here, and let's say this one is A, for example. So that's A sitting right there, and we have the pulley connected, so it goes over the pulley. These are not going to be equidistant, by the way, and so we have a cart 2, which we'll call B, sitting out over here, and then we have our whole setup. Now, with this in mind, if we label one side, let's say that we have X over on this side, just for kicks. I'm not saying you had to put it there, but if that's X, because this is going to be different distances from A to the pulley and B to the pulley, so then that means this would be 39 minus X. And why is that? Well, we know the rope is 39 feet long. So if you use X units on the one side, that means there's 39 minus X on the other. And we have some distances here that we don't quite know yet. So let's just label this one from A to Q. Let's call that Y, and then let's call this Z right here. So now we have a whole diagram that's labeled. We might have some information that we can use, but at least we have some sort of standard to where we can work with this. Okay, so now information that we can use here. Let's see. So we already used that 39 minus X with the rope there. We're going to have, we have cart A is being pulled away from Q at a speed of 2 feet per second. Okay, so cart A is being pulled away. So that means we're going to be heading this way. If it's being pulled away, we'll have this be the positive direction. Okay, so everything heading in this direction is going to be positive. So heading towards Q if you're B, heading away from Q if you're A. So if that's the case, what we know by that 2 feet per second is that we have dy dt equals 2 feet per second. Now we want to know how fast is cart B moving. So looking for, when we're talking how fast, right, that means we're talking a rate of change. So that means the rate at which z is changing it with respect to time. Looking for dz dt when z equals 5 feet. Right, so that's the distance from Q. Okay, and as always, if there's any questions, there's a chat box. Please ask those questions if you're getting hung up on an issue here or something like that, these problems can be quite technical. But I just want you to see how we kind of think through these. And I'm not going to have the most straightforward argument. I'm just trying to have you see how do we kind of organize our thoughts, how do we kind of break this problem on down. Okay? So in this one, where can we go from here? Well, we have a couple equations. If you notice, we have a right triangle on actually two right triangles sitting right there, and the 12 is a constant versus the x, y, and z's. Those are all variables. Those things are changing with this pulley. So let's actually write down two equations and we can see with what we can work with to go from there. So notice the 12 is kind of our mainstay. We have in one scenario we have y squared plus 12 squared equals 39 minus x, the quantity squared. In equation 2, we would have, using that triangle on the right hand side, just Pythagorean theorem again, z squared plus 12 squared equals x squared. Right? So that second equation looks pretty nice and easy, and maybe we can work with that, because ideally what we're looking for is that dz dt. So I'll circle it here. We're looking for dz dt. So that means we're going to need to take a derivative of this second equation. So we're going to take a derivative with respect to t. Okay, so the way we can go about doing that is, well, we're going to have to use a chain rule. So you have z squared plus 12 squared. Remember, 12 is a constant, so that's going to be an easy one for us, equals derivative with respect to t of x squared. Okay, so what do we get? Well, notice that gives us 2z dz dt, because of the chain rule right there, plus 0 equals 2x dx dt. So notice we can build that to a solution for dz dt. Just by dividing by 2z, you get dz dt equals 2x over 2z dx dt. Or in other words, we get dz dt equals x over z dz dt. Okay, so we have a setup now, right? We have dz dt, which is what we're looking. Oh, that should have been a dx dt. Sorry, so that's a dx. We have a setup now in terms of things we can find, but the only piece of information where we really have a solution for right now, we have dz dt. We don't have dx dt. We just have that z will be 5 is when we want that value. So we'll put the 5 in for right now. So I'll switch colors, and now we'll kind of go to the red. So we're looking for this x, we're looking for this dx dt. So we're kind of stuck. But this is where we can use the other equation, right? So we have another equation. Y squared plus 12 squared equals 39 minus x, the quantity squared. Okay, well, maybe we can build to finding that answer. Well, in order to do that, first off, we can take the derivative, maybe, and see what happens. So we'll go d dt. And actually, there's a method I could use to find x right away, as a matter of fact. Actually, which would you all prefer? Would you prefer I find x right now? Or would you prefer I wait a minute and then we'll find x? What would you all like to see? Any ideas? You can go ahead and put it in that chat there. So actually I will find x before we go on to that second derivative, because we can find that with just our original equation. So if we go back, before I go back to there, I'll go and we'll find x right here. And the way we can find x, we know z equals 5. So when z equals 5, that means we have 5 squared plus 12 squared equals x squared. 5 squared is 25, 12 squared is 144. You add those two together, I believe you get 169. So 169 equals x squared, but we need to take the square root, and we only worry about the positive version. Yeah, so find x, this sounds good. I'm right on the right track. There's a little bit of delay too, so you will see a little gap between when you write it and when it actually appears. So I saw a couple of them now. So now we have the square root of 169, so x equals 13, right? So that means dz dt, as of right now, we have 13 over 5, right? And then times dx dt. Questions thus far? Okay, so now what we want to use is we want to try and find our version of dy dt, right? Okay, so if that's the case, I made a mistake here. Hopefully y'all can see the mistake. How fast is cart B moving toward Q? I read it as cart B being 5 feet. My apologies. So this should be cart A is 5 feet. So that instead of Z equals 5 feet, that's going to be Y equals 5 feet. So we don't have this being 5 just yet. We'll deal with that in a second. So I can fix this. So we'll leave it as X over Z. There's a simple fix for this though. So now going down below, the formula is still the same. You get dz dt, that's still what we're looking for. It was y equals 5. My apologies, I missed the cart A. That was the big thing. So it's when y equals 5. We have 5 squared plus 12 squared. Once again, we're using this equation 1 once again. So that equals, instead of x squared, that's going to be 39 minus x squared. So that means when we go here, oops, my apologies once again. So square root of 169 equals 39 minus x. And so that means 13 equals 39 minus x. So in that case, we get x equals 26. You add x over to the left-hand side and subtract 13. So now, going back to the dz dt, my apologies for that. So this equals, so now we have 26 over, we'll deal with z in just a second, in dx dt. So a little bit more work. Now we can get z. That's not too bad. So find z. We can go back to equation 2, and so that's where we get z squared plus 12 squared equals 26 squared. So that's not going to be the prettiest thing of all time, but hopefully we can kind of work this out. This gives us z equals the square root of 26 squared minus 144. And I mean, you can leave it as that if you'd like. If you wanted to, you could probably figure out what 26 squared is and then get your answer. I believe, what is that, 676 maybe? So yeah, that'd be square root of 676 minus 144. This part wouldn't be necessary come test time. You could always leave it as is. And so this means z equals the square root of 532. So what that means now, dropping this formula on down, we have dz dt equals 26 over the square root of 532, and then dx dt, whatever that'll become. Yeah. Oh, thank you for the 532. I appreciate that, Raven. So now let's go from here. So what do we want? We have equation 1. We can do the same derivatives rules to try and figure out dx dt, and once we have that, we're pretty much done. So we get d dt of, it's going to be the same pretty much derivative with exception to that one right hand side. So y squared plus 12 squared. So then we have equals d dt of 39 minus x, the quantity squared. Okay, so moving forward from there, what do we get? Well, this will give us 2y dy dt, which we do have some information about, equals 2 times 39 minus x, and we know what x is, right? Recall a couple steps up above, x equals 26. So, and then times dx dt, and times a negative 1 as well. Okay, so now moving forward from there, we can take that, notice we have 39 minus x, that can become 13. So this thing becomes 2. We know y equals 5 at that point, I believe. Yeah, y equals 5 feet. So 2 times 5, and then we have 2 times 13 dy dt equals negative dx dt. Right? Okay. And so from there, what happens? Well, this means that we get, the 2's will cancel, and dy dt is, oh, we'll move the negative over there. So dy dt is 2. And actually, let me do it this way. Rather than, I originally called it positive, let's call that negative. Just for kicks, because it's moving away from Q, that'll make our life a little easier here. So that'll be negative. That means this will be, because I kind of screwed up what I was starting with. So toward Q would be the positive direction. So now, taking a look at that, just that little change there. So we get negative, and then we have 5 over 13 times 2 equals dx dt. So this gets us ready for that final answer, and hopefully I can fit it on the page here somewhere. So we have, with our final piece, dz dt let's see, fit it in here. dz dt equals be 10 over 13. Oh, and this was negative 2 now. So that'd be positive 10 over 13. Whoops, we had the other piece first. So the part that I'm looking at right here is 26 over the square root of 532 times just 10 over 13. And that would be it. So, and if you wanted to simplify that, you can make it the 26 and the 13 would cancel off and give you 2, so just 20 over the square root of 532. Okay, so kind of crazy. I know how you see how this works, and I'm trying to deliberately have this be a bit messy in terms of I want you to see just the thought process of, okay, so there's going to be a struggle, right? And that's okay. We just keep on working until we can find a solution, find the values that we want, and things like that. So all you saw, I mean, I was just working with Y and Z. Luckily, I caught that cart A part. That's something that happens from time to time. You got to make sure that, hey, double check our numbers, make sure they're working out, stuff like that. So, but draw the diagrams and you see how we can kind of work from there. It's just basically plug and chug away until you can kind of get to the piece you wanted. In our case, it was dz dt. Right, that's the main thing that we were looking for. So as soon as we knew we were looking for that, just chip away, chip away, chip away until we get there. So hopefully that made a little more sense on that one. We'll try another related rate problem. So Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure P and the volume V satisfy the equation PV equals C, where C is a constant. Suppose that at a certain instant the volume is 600 cubic centimeters, the pressure is 150 kilopascals, and the pressure is increasing at a rate of 20 kilopascals per minute. At what rate is the volume decreasing at this instant? Okay, so it doesn't look like we're going to need a drawing in this one. It looks like the formula is even given to us, so that makes our life a little bit easier. So we have PV equals C. But the big thing that I like to point out is this C. Anytime you see something labeled as a constant, make sure you know that, because what that means, if that's a constant, that means d dt of C equals 0. Okay, so keep that in mind. That's going to make our life a little easier here. So the other information that it's given, what else do we have? At a certain instant, the volume is 600 cubic centimeters. The pressure is 150 kilopascals. Okay. So our given is, all of those scenarios are when we're looking for a certain piece of information. So we're looking for, in this case, if you notice, the volume decreasing. So that means dV is the volume decreasing. So dV dt, we're looking for how that changes when we have a few pieces of information when that's occurring. So the volume is 600 centimeters. So that's V equals 600 cubic centimeters. I'll be a little bit more careful this time rather than the A's and the B's and all that stuff. So the pressure is labeled by P, and so that's 150 kilopascals. And then the pressure is increasing. So since we're talking increasing, that's dP dt equals our value being 20. And notice that's where we're going to get minutes involved with this too. Are there any questions thus far? If so, please ask. You know, and that's what I'm here for. That's the main thing. So we have our three pieces of information. So now we want to take the derivative. So you take d dt, PV equals d dt of C. We already know one of those derivatives. Can someone tell me what rule we need to use on the left-hand side in order to take that derivative? Any ideas? So we have a whole bunch of derivative rules, and this one gets a bit trickier because we have different variables listed here. So we have a P and a V, and they're multiplied. Anyone know what rule that we need to use in order to take that derivative? Very good. So Carlos, please send me a nice little email reminder. You're going to get a bonus point on this because you got it. It is the product rule. So in fact, so the product rule, how does that go? That goes d dt. Luckily these are just raised to the first power, so it's not going to be it's going to be a pretty easy calculation as long as you remember it's a product rule. So we have that going on for our derivatives. The derivative of the right hand side equals 0. Okay. Now what does this mean? So from here, what do we get? Oh, I forgot one last thing. Actually, I'm going to go back after I'm done with this. I want to put one last thing on. I got a little ahead of myself with the final answer. I forgot to put it on there because I'm so used to having the blanks there for putting that in. I want to put a label on this too. So notice though, what happens is we get dp dt times v plus p times dv dt, and that equals 0. Okay, so moving forward from there, and actually, Raven, I saw your chain rule too. That's technically going on as well. If we had more steps involved, so you got the right idea. A lot of times the chain rule is involved because we're doing the DDT. So I'll also give you a bonus point for that as well. So that's the right idea most of the time. It is the product rule though, is the main rule that we want to use in this case. So good though. I'm glad you all chiming in and kind of getting those answers out there. So it's very good. So moving forward now, we just want to plug and chug basically. So dp dt is 20, right? We have our volume somewhere here, 60, or no, 600, sorry. P, that's 150. And then we have, I'll put it in parentheses just for kicks, and 150 times dv dt. That's what we're looking for, so this is just going to be basic go ahead and solve. So we get 150 dv dt equals 20 times 600. And a lot of people want to try and actually multiply that out. I'd recommend waiting in this case. You don't have square roots and stuff involved, so go 20 times 600. Oh, this should be negative over on this side now. So negative 20 times 600, all divided by 150. Now, why is that important to just keep it waiting? Well, I'll kind of show you. Notice the zeros cancel. 60 divided by 15 is 4. So I can go this way and that way. It leaves me with 4. Negative 20 times 4 is negative 80. Okay. And then remember, so we had cubic centimeters, and then we were talking minutes here. So this is going to be cubic centimeters per minute. You can kind of see it right there, so not a big deal. But I want to make sure that you're aware this is how you can derive what our labels will be at the end of the day. So notice it's negative, so that means it is decreasing. So decreasing, the problem actually wanted at what rate is the volume decreasing? Decreasing at a rate of 80 cubic centimeters per minute. Okay. So hopefully that makes sense on that. And good work there. So what I forgot to do on the last time, I forgot to put a label on that last thing. So I don't have an actual number. I know it looks kind of crazy, and that's fine. You can insert these, and these are fine final answers for what you're looking at. So you get 20 divided by the square root of 532, but it's feet per second. Okay, so just keep that in mind in terms of what's going on there and how we work those problems. So labels are important, and they help us kind of guide us to the answers and whatnot. So moving out of the related rates, we saw a couple of those, and don't worry, we'll have plenty of other stuff. And if you want more related rates, I will be doing a review for the final, so you'll see them again there. And you can also post those questions in the YouTube live reviews. I'll be happy to answer those there too. So now, find all the numbers C that satisfy the conclusion of the mean value theorem for the following function and interval. Enter the values in increasing order, and enter, we don't care about that part. So you care more if you're working on a problem on woodwork or something like that. So what does the mean value theorem state? So the mean value theorem states, first off, we need something to be continuous and differentiable on that interval. So this function f is continuous and differentiable on the interval -1, 1. Now, why can we get away with saying that? So what's the whole idea here that allows us to get away with saying that this is continuous? Why did some wizard come down and say, oh, this is a continuous function? No, it isn't like that. There's a reason. We have some some rules that we were able to do earlier in the semester. And this is in fact a polynomial, and we know that all polynomials are continuous. So that's why we can get away with saying that, right? Alright, so with that in mind, the mean value theorem states then what we can do is we can go f of 1 minus f of negative 1 all over 1 minus negative 1. There's something in the interval. So mean value theorem basically states that there exists a c, and I'll put at least one c. Sorry, that was supposed to be a parentheses on the left-hand side. Sometimes my pen has a mind of its own. Okay, so there exists at least one c in that interval negative 1, 1, such that, well, technically I could include the endpoints too. F prime of c equals that slope of the secant line. So this is basically a secant line is what we're looking at. So now, moving forward, oh good, I saw that f of x is a polynomial. That's exactly why we're getting away with that. That's awesome. So now, f prime of c, let's see if we can figure this out. So first off, f of 1, f of negative 1, and then 1 minus negative 1, we know the bottom's going to be 2. Plus 2 times 1, plus 7. And if you want to work this down below, that's fine, you can. Minus f of negative 1, so it goes 3 times negative 1 squared. Plus 2 times negative 1, and then plus 7. Okay, and that should equal f prime of c, which we'll deal with in a minute. Now the beautiful thing here is if you square negative 1, that becomes 1. So if you square 1 and negative 1, they're the same thing. So these two parts would cancel. The 7s will cancel. Now notice we have 2 minus a negative 2. That makes 4. So this is 4 divided by 2 equals f prime of c. All right. A lot of people get hung up with trying to add up all these things, and you're going to have a lot of stuff cancel from time to time. So try and take advantage of that. Oh, this is a great question. I love this one. So the question was, would it matter if you did f of negative 1 minus f of 1, and then you go negative 1 divided by negative 1 minus 1. I'm assuming those were in parentheses there. So yeah, actually that's legit. In terms of the interval, notice you're looking for just the slope of the secant line. So if I multiply both, let me kind of show that. I'll show this in blue. That's actually worth kind of denoting. So notice if I multiply the top and bottom by negative 1, let's see what happens, right? So we go f of 1 minus f of negative 1, and I'll erase this there in a minute to give ourselves some room here. Okay, so what happens? Well, notice if I multiply, this does not change the equation whatsoever. Okay, so because negative 1 divided by negative 1 is 1. So notice what happens. So we get negative f of 1, minus a minus makes a plus f of negative 1, right? And then we have all over, well, this becomes negative 1 plus a negative 1, right? Now I'm going to just rearrange these. So I'm going to move this to the front and move that to the front. And so notice we get f of negative 1 minus f of 1 all over negative 1 minus 1, right? So you get the same exact value, and all you did is you just rearranged. As long as you're consistent, the only thing I can't do is I can't have f of negative 1 and then go 1 minus a negative 1, right? So if I go f of negative 1 in the first position, that down below I have to have a negative 1. So as long as you're consistent that way, you're good to go. So hopefully that makes sense. That was a great question. Awesome. Those are the types of things we're looking for here. So any questions on that now, or does hopefully that makes sense? So yeah. So it doesn't matter. You don't have to be hung up on what order you're going to start. Well, which point do I? No, that isn't a big ordeal. You're just looking for the slope of a secant line. And I'm going to illustrate that. The next problem I was trying to I have coming is we're going to actually look at a graph, what's going on. Okay, so we get this whole thing, what we've led down to is 2 equals f prime of c. And the whole problem says find the whole c value, right? Whatever. So, and we'll make sure it fits in here and whatnot. And it should, right? Because this is continuous and all that. Alright, so in order to do that, we need to find first f prime of x. Well, f prime of x, we can use the power rule. So you get 3 times 2x to the first power. If you struggle with the derivatives, please let me know, and I'll be happy to show those a little bit more slowly, but I'll move through some of them pretty quick. So you get 6x plus 2, right? Okay. So you get 2 equals, notice, oh, this is going to be kind of cheesy here. So 2 equals, oops, let me get a little bit of, before I get ahead of myself, f prime of c then would be 6c plus 2. They want c, so we'll solve for c. So notice, if we're solving for c, it's going to be kind of silly. 2 minus 2 would make 0 equals 6c. So if that's the case, then we get divide both sides by 6 and c equals 0. Okay. So hopefully that makes sense on that one. Kind of a silly answer, but it starts to make a little bit more sense when you start to think of what's happening with the graph at that point. So yeah, and notice this is inside the interval -1, 1, so we're good to go there. So, and that's it. There is no other values in terms of inside that interval where it happens. Okay. Questions on that? So, all right. Now we're going to have some fun here. This freaks people out because we have a graph. Oh my gosh, it's a graph. Well, if you understand what the mean value theorem is actually stating, it does become a lot easier. So, and that's what we're going to focus on is what's actually happening here in terms of our function. So we have this function graphed, and does the function satisfy the hypothesis of the mean value theorem on the interval AB? Notice this graph is a smooth curve, right? And so our answer, I don't know what the drop downs were, but the answer is yes, since the function is continuous and differentiable on the interval AB. Okay? So we have the continuity and differentiability on that interval. You can change that to the closed interval as well. So now, here's the next question. Does it satisfy the conclusion? Well, it should, right? Otherwise, the mean value theorem isn't going to work. But just to illustrate it, I'll kind of show you what's happening. So there's 2 points, right? Here's the point A on that curve, and then it wants the point B on the curve. Okay. So now what we'll do not let your eyes fool you. I'm going to try and draw the best straight line that I can without screwing this up. Hey, look at that. That's pretty good. I'll take it. So there, we have a line going right there. Okay, so now let's start to take a look at the graph. What are we trying to see? Well, we want to try and see where a value of a tangent line would look pretty similar to that. So now notice we'll start with n. If I were to draw the tangent line of this, notice I get the graph going like that. That's not going to have the same slope, right? Because one has this value being 0 for the slope. So let me write m equals 0. In this case, actually, if I know the distance from it, I'll just put m equals question mark. I don't know because I have b and a. I don't know what each tick mark is worth, to be honest with you. But so, and then in the other case, I'll do where p is, right? Well, notice the slope of this thing. Oh, my line here isn't as good, but the slope of this one is decreasing. So I know that isn't going to work, right? So it has to be somewhere in this interval. And I'll even start in some earlier positions. We'll put in orange right here. Notice that's too steep, right, for this curve, right, for that tangent line. So that isn't going to work either. However, let's pick green this time. This one's for Kermit the Frog. Okay, let's try and draw this line. Wait a second. I might not be the best at drawing lines, but if I draw something like that, notice what happens. These two lines, if I'm to draw this, this would be like a right angle here and here. These two lines are parallel. So parallel lines. I'll switch back to the black so you can see it a little bit better. So these lines have the same slope. And the reason why the mean value theorem works this way, right? Notice we go and we're increasing at a faster rate than what this value is right here. Sooner or later, though, we got to go from some positive number that's greater than what this average rate of change is to a negative value, right? And so we got to hit every number in between in the derivative. So we have to, in fact, hit the same slope as the slope of the secant line. So our actual thing is, yes, and it actually occurs at x equals m. At what point c is f prime of c equal fb minus a all over b minus a, when our answer for this is when x equals m. Okay? So that's the big picture as to what's going on with these things. It's always, you're going to have something having that slope of the secant line. Are there any questions on that piece? Because this is a tricky concept for a lot of people, but if you use the graphs, it does wonders for you, and it helps out tremendously. Okay. If you do have questions, please let me know. I'll be happy to answer them. And so moving forward from there, though, we're going to move into L'Hopital's rule if I don't see any more questions. If you do, as I said, always just pop up the question, and I'll be happy to answer it when I see it. Okay. So moving into L'Hopital's rule, and why do I say this is L'Hopital's rule? So I'm not even looking at all this junk, to be honest with you. I don't care about all that. All right, suppose you have two linear functions, f and g, as shown in the figure. Then the limit as x approaches a of f of x and g of x. What the heck is this? Now, we have a, and then it's saying, hey, which function's f of x, which is this top function is f of x, and they're saying which function, oh, you see it right over there, the g of x as well. And then that means that this looks like an intercept, so this is when x equals 0, right?